Welcome back, folks. So in this video, I wanted to introduce exponential growth, and I really want to compare it to what we already know about linear growth. So we have two scenarios here. In one scenario, scenario A, Deanna and Christy have a little bunny sanctuary where they rescue bunnies, we'll say. So Deanna and Christy, they start off with 4 bunnies on their sanctuary, and every month afterward, Christy is able to rescue and bring back 2 more. For scenario B, Justin has 4 bunnies on his bunny reserve, and so he doesn't bring bunnies in. He just lets the bunnies kind of do their thing, which means that they have some babies. Okay, and so we'll say that he starts off with 4 bunnies as well, and every month thereafterward, the bunnies pair off and have two babies each, 2 babies per pair. Okay, and what I want to do is just compare their growth, and I also want to create an equation for both of them. So for Deanna, you can probably kind of see, we're going to assume that I guess the bunnies in Deanna's scenario are sterile. They're not the same bunnies as Justin. So for Deanna, the bunnies don't have any babies. They're just all rescues. So for Deanna and Christy's bunnies, this is actually not meant to be particularly challenging or tricky in any way. We're simply starting off with 4 bunnies. Every month we're adding 2 more. And so this grows linearly, right? So we're at +2 each month, and that's indicative of linear growth. I'm not gonna say it just grows by 2. I want to be really specific here and saying exactly how does it grow, because adding is not the only way something grows. Although I suppose you'd be right in saying that is typically what we think of. If I said it grows by 7, you would probably assume it adds 7. But I just want to be really specific now, especially when we're comparing exponential and linear growth. Okay? And by the way, I've thrown around linear or exponential, the word exponential a lot. We'll also define exactly what that means here. I think exponential is a word that gets used a lot. But for math, at least, it's very specific about what it means. So I'm going to represent Deanna's bunnies with D of X. D of X representing the population, and X, of course, representing the month. Okay, for Justin, it's going to be a little bit different, and so it's going to be not inherently obvious, and so I want to create an equation for this. Okay, or sorry, I want to draw a picture to represent this. So we'll start with month 0, then we'll go to month 1, and so forth. Okay, so month 0, as it says here, he's got 4 bunnies, so I'll just draw them with little bunny heads like so to represent that. Okay, now on month 1, well, they're still there. No one escapes or anything like that. No one dies off, we'll say. Okay. The way this works in this scenario is that, well, every pair of them has 2 babies. So the way I'll draw that is I'll say that these 2 kind of pair up. I'll draw the babies in a different color if I can. Okay, there we go. Sorry about that. So we'll draw them. These 2 have 2 babies. 1, 2. And these 2 have 2 babies. Oops, 1, 2, like so. Okay, so on month 0, we have 4, and on month 1, we have 8 of them. Okay, so you might think, okay, maybe it's +4, +4, but just having 2 data points is not nearly enough to create a pattern. You would need at least 3, and of course, the more the better. But we're just going to do 3. So we're going to go on to month 2 here. Month 2. And let's see, well, at this point, we have 8, we'll call them parent bunnies. So I'm going to draw on there 8 bunnies. There's 8. Sorry, there's 4, and now there's 8. And of course, now we have 8 of them. So there's going to be 4 pairs of them. So I will draw them pairing off. Like so. And again, each of those pairs is going to have 2, like so. So I'll try to speed this up here. Copy paste, copy paste, copy paste. Okay, cool. And so now we have 16. And so we can see here, oh, sorry, my face is kind of in the way there, but notice that all the parents, there's basically the same number of babies as parents every single time. And so the population seems to always be doubling, right? To get from 4 to 8, we'll go times 2. From 8 to 16, we'll again go times 2. When we see this constant multiplication, that is indicative of exponential growth. So let's define that. So linear growth, or I guess, yeah, linear growth is growth by constant addition. So in this case, or in Deanna's case, it's plus 2, plus 2, plus 2, and so on. Whereas if we have Justin's case, where it's times 2 every time, it's growth by constant multiplication. Growth by constant multiplication. Okay, so that's what exponential growth means. Okay, again, I think it's especially like in everyday speak, people throw around the word exponential just to mean it grows fast. Oh, and exponential growth does grow fast, but it's more than that. It's not just it grows fast. It has to grow by, multiplying times 2, or times 3, and so forth. Alrighty. So let's actually see if we can create an equation for this. And again, what I want to do is, to help us with that, is I want to compare it to linear growth. So I'm going to create a table here, and we're going to represent the months. We're going to represent D of X, representing Deanna's bunny population after a certain month. And then Justin's, we'll abbreviate with J of X. Okay? So month 0, 1, 2, 3. And then we'll go all the way down. We'll try to generalize that to month X. Okay? So with Deanna's, again, we start off with 4. We're adding 2 every time. So we'll go 6, 8, 2 plus 2 plus 2. Oh, yeah. 10, and so forth. Right? We already know, again, D of X is equal to 4 plus 2x. Okay? Again, figure 0 is 4. Our growth rate is plus 2, so it's a linear function, and we're familiar with that. Notice I did change the order a little bit. That's not necessary, but I think it helps for this, at least this example. Again, Justin's goes from 4 to 8 to 16, and if we follow the pattern times 2 again, it will go to 32. Now, our question is, what is Justin's equation going to be? All right. I'm going to write it out like this. So what I'm going to do is I'm going to rewrite all of these values for Deanna using the equation. Here's what I mean. So I'm going to show, okay, again, 4, well, that's 4 plus, and then how many times, well, since we started off with 4, how many times did we apply our growth rate to it? So in this case, plus 2. In this case, we applied it 0 times, right? So it'd be plus 2 times 0, right? After 1 month, we applied the growth rate 1 time, right? Plus 2 1 time. And so we can say it's 4 plus 2 times 1. We added 2 only 1 time. If I'm starting off with 4, how many times did I have to add 2? How many times did I grow to get to 8? Well, we took 2 steps, right? 1, 2. And so we can say 4 plus 2 twice gets you to 8. And likewise for 10, we start off with 4 and add 2 3 times. Notice here that the x value, whatever x is right there. That's telling you how many times you apply the growth rate. Okay, I'm bringing this up because it's going to be very, very similar to Justin's. Okay, so we're going to start off with the same figure 0, right? So we start off with 4. Okay, well, that's whatever it is. Okay, now how many times did I apply the growth rate to get from 4 to 8? Well, I only did it once. But remember, the growth rate in this case is not plus 2, it's times 2. So I'm going to do 4 times 2. How many times did we multiply by 2? Well, we only did it 1 time. So it seems a little extra, perhaps. But I'm going to apply a 2 to the first power there. Now, you notice I left the 4 blank because at first it didn't really make sense to put it there. But we can use a similar idea here. If I started off at 4, how many times did I apply my growth rate to get to 4 and stay at 4? Well, I applied my growth rate of times 2. How many times? 0 times. I haven't done it yet. And yeah, 4 times 2 to 0, because 2 to 0 is 1, remember, is still just 4. So this still works out. And again, notice, because you're applying constant multiplication or repeated multiplication, I'm not doing 2 times x like it was over here. I'm doing 2 raised to that power instead, because you represent, for addition, you represent repeated addition with multiplication. Repeated multiplication you deal with, you represent with exponents. So over here we have 4. Again, we started off with 4, and how many steps did I take? 1, 2. So I applied my growth rate times 2 twice. And likewise, 1 more time would be 3 times. And so we can see hopefully we can see our x values right there as our exponents. And using a similar pattern, we can see that our function hopefully is 4, because again, that 4 is always there, times 2 to the x power. Okay. I think this is really, really neat, especially when I leave it next to my linear function, because if we compare them, they all have the same components. This part right here, the purple part. So let's see. Let's compare. Linear, exponential. They all have the same parts. So again, this 4 is figure 0, right? Or the y-intercept. So I'll call it, figure 0. Well, maybe I guess I'll use y-intercept to make it maybe a little more universal. Y. Look. The y-intercept. Okay. Now this part is what changes, because this grows by a constant addition. You're adding that growth factor. So we're adding plus, whereas exponential you're multiplying. The 2 in both of these cases is the growth rate, I'll say, right? It just means slightly different things in different contexts. So with linear, again, it's adding, and the exponential function, it's multiplying. So in this case, I guess I'll just underline it. I guess we'll do in green. That's the growth. And this is the growth. And the way you represent repeated growth changes. Again, with repeated addition, you represent with multiplication. So that's why it's times x. With exponential, you represent repeated multiplication with exponents. And so that's why the x ends up as an exponent there. And then, of course, that's y equals. Y equals. Okay? So hopefully this helps you see, like, an exponential and a linear function are very, very similar. An exponential function, I like to think of it as kind of like a quote-unquote upgraded linear function, where, like, you upgrade addition into multiplication, and you upgrade multiplication into exponents, if that kind of makes sense. That might be a little weird. I don't know, my brain works in weird ways sometimes. Okay? But that's how you create the equation of an exponential function, assuming you can get the y-intercept and the growth rate.